which the in situ generating here two small amount of each allelic reaction. Okay. Allelic tertiary alcohol forms intermediate. What kind of intermediate? Sunshine? What kind of intermediate? 답은 맞췄는데. Daniel, what kind of intermediate? 영경? 동은? 그래서 카보케라요. 카보케라 intermediate. That's what we are going to cover. 이 생각이 없었는데. 자, 보시야. 카보케라 intermediate. Only option is here, secondary alcohol. It cannot be 1 bromo, and it could be 2 bromo. And there is alcohol attack first, and then bromide comes back and replace those OH with activating of OH. Okay, that's a Grignard reaction, and that generates not electrophile, that generates a nucleophile. Okay? You can reach nucleophile. Okay, halide is electrophile. Delta plus. Change that by adding magnesium or lithium to make nucleophile. We need what reaction? Grignard is the name. The general reaction, acid reaction, base reduction, oxidative insertion, yes, correct. But what happened to the carbon? Oxidation or reduction? It's reduced. That's getting more electron, so it becomes C plus, from C plus to C minus. That's a reduction to the carbon. That's how you can change electrophile into nucleophile. Did you say that's a nucleophile? Yeah, if there's a nucleophile here, then that may be easy question. But now that nucleophile, Grignard reagent, can react with the water to make alkane. So that one, what we are going to talk today too. Nucleophile can be base. Usually base is nucleophile. Even same material sometimes act as nucleophile, sometimes act as base. Base electron rich, nucleophile electron rich. They do not give that electron permanently to the partner. That's why it's not reluctant. Okay? That it carries that electron, and when they leave, they carry out that electron. It's like acid-base base. Base, nucleophile, they are similar, but sometimes they are nucleophile, sometimes they are base. We are going to see that today. That make alkane. Where is the halide here? Okay, there is a halide, okay. For Grignard reagent C minus, that react with water's proton to make very the cheap solvent, side reaction. Partner of proton, proton is acid, right? Proton is acid. Partner of acid, base. That's has the extra electron. If it attack a carbon, then we call that nucleophile. If that attack proton, that act as base. But that's the difference. Electron-rich species, it has two options. React with electron-deficient carbon, electrophile, or react with acid. That's also electrophile we call, but that's separately, it's not carbon, that's acid. That's why Grignard reagent can be base or nucleophile, depending on what is the partner of the reagent. I told you, lithium Grignard reagent is similar. Closed shell metal, magnesium, lithium plus closed form is like very hard billiard ball. That's a hard nucleophile. That's why they react better with water, H plus. Okay, that's it. The exchange reaction, exchange of metal, lithium with a copper, and make that soft nucleophile. Lithium was a hard nucleophile. Copper is a transition metal, which has some empty the d orbital. Electron is more flexible. It's a soft nucleophile. That's why it reacts better with the carbon electrophile. What's wrong with this reaction? This reaction looks like it's a substitution reaction, but aromatic is attached together. It's carbon-carbon bond formation. It's not elimination. Specifically, this alkyl-boronic acid and alkyl halide, that reaction is called as Suzuki coupling. So following the chemist's name. And palladium in this case, inserted and eliminated. That's catalyst. That is the most complicated reaction in the chapter, but that does not mean that you don't need to know that. That's the only example we show you. You need to study. Last question. insertion. Which one is oxidized? Carbon was oxidized. I asked the same question 3 minutes ago. Carbon was oxidized, reduced. PD was oxidized from 0 to +2. Okay, oxidative insertion. And the last step, PD is removed to go back, reductive elimination, removed. Okay, so first step was oxidative insertion, and last step, palladium is removed by taking the 2 electrons reductive elimination happens. Okay, that is the cycle of the palladium things. Okay, based on this, now we're going to move to most challenging, most interesting topic of organic chemistry, SN2. Yay! Okay, so now we are going to study about the reaction of alkyl halide. Alkyl halide, electrophile. It has a delta plus. And the reaction we have seen so far seems like electron-rich species and electron-rich leaving group, they are exchanged. So that's why this reaction we call substitution reaction. Similar reaction, similar the reagent, looks like the same reagent. Now, in this case, OH minus, they attack from behind the leaving group, coming here, attack here, and then push this out. Okay, that's SN2 reaction. Now, this type of reaction, H and Br was removed. So type of reaction was this elimination reaction. What happened? This OH approached from here, from this direction, north, south, east, west. Don't I give up? OH is approaching from which direction? North, east, which direction? OH is coming from which direction? Northwest. From this direction, come here, attack here, push this out. That's SN2. If that attack, not here, if it attack here, from same direction, attack here, this electron is pushed and pushed. That's the problem here. If that OH attack carbon directly, that's a nucleophile. If that attack proton and generate the eliminated product, what is the role of that OH? What is the role of the OH? If it's not nucleophile, what is it? It's a base. Okay. Same species which has electron rich, it can attack delta plus of carbon, or it can attack proton. So that's why sometimes the nucleophile can be base. Okay, many of the base they can be nucleophile. So the differentiation between base and the nucleophile is their role on the reaction. Okay, this is a two type of reaction we are going to study today. Now that's why. So by looking at this kind of reactions, here starting from alcohol, PCl5 or PCl3, it's the same reaction I said. First step was attacking here, and then chloride is removed, coming back and attack here, and generate chloride product. And base with the water, you can generate in situ OH minus. OH minus attack here and generate coming back to the acid, the alcohol. So it's not strange, but by looking at those particle activity, very funny, this is replaced by Cl, and this is replaced by OH, and these two is enantiomer. Hydrogen inversion happened. And if we keep going, starting from this and Cl reaction, and this one is also enantiomer. And coming back to the original structure. So it looks quite interesting. What could be the mechanism of these reactions? That is the starting point of studying of this substitution reaction. Here I can highlight electrophile, delta plus, delta minus. Electron-rich species come here and then generate this one. It's the exchange reaction. That's why we call this S reaction, substitution reaction. Okay? Meaning exchange. Then what could be the mechanism? So to study that, now another activating group appear, tosylate. In this case, the reagent is a tosylate chloride. We have seen similar things before, SOCl2 and PBr3. It could be PCl5, so N3 or 5, both of them similar way they work. OH attack first. Last time we have seen to activate the OH attack here first. And then chloride is removed. Chloride comes back, attack from behind. It makes a kill chloride. Similar reactions happening here. OH attack here first. Br minus is removed and come back from behind attack, make in this reaction, OH attack, Cl removed. In those cases, those intermediate is very unstable. That's why chloride attack right away. But this intermediate is relatively stable, so you can isolate. So this OH attack tosyl here, and then this group Cl is removed, and then this tosylate is generated, you can isolate. Isolate, and you can use a different nucleophile to attack. In this case, the nucleophile is acetate. This is acetic acid. If you remove proton, leaves anion. So this one is electron rich. So this can attack as a nucleophile. This attack that tosylated position from behind. This is tosylated here. Now this attack from behind, attack here, and push this out, including this accident. Their reaction is very similar to this. But these are two-step reactions. And then this acetylate is added here. Now it can be, this is ester, and ester can be hydrolyzed by adding water. That reaction you will learn in the next semester. But anyway, it can be hydrolyzed here and generate the OH. Now after this reaction, very funny, starting material here, and then this product here, both of them are OH. What is the relationship between this and this? What is the relationship between starting material and this? That's enantiomer. The configuration of the chiral center is inverted. It was originally like this, now it becomes like this. Product is the same, OH group. Now if you repeat that reaction, alcohol react with the tosyl chloride, and then adding tosylate. And again, same reaction, acetate attack here, and then generate this one, hydrolyze, come back. Now this means something. It's not a random reaction. Now the hypothesis is, during this reaction, this is tosylate, activated alcohol, acetate attack, and generate this one. And apparently this configuration, if there is originally one, let's say R form, then this becomes the S form. This configuration was like this, it is changed like this. That reaction should happen together. It's not carbocation intermediate. Then those kind of reactions is discovered further and further. Let's say if you have this alkyl bromide, this is the chiral center or not? This is a chirality center or not? Yes, because it has a 4 different H, methyl, phenyl, bromide. Here we have seen similar nucleophile before. Carbon-carbon triple bond, and you can remove proton. You can make acetylide. Similar way, cyanide, Cn minus is also good nucleophile. If that attacks here, what do you think? The stereochemistry inverted or not changing? If you attack with this here, there is also changing. So if it changes, we call inverted. Okay, this is inverted like this. If it's not changing, then retained. Now this type of reaction. Now the mechanism was suggested as SN2 reaction. S substitution and nucleophilic reaction. 2 bimolecular reaction. That means if this type of reaction happens, 2 reactants. And if you check those reaction rate, if you increase OH minus concentration, then reaction rate is also increased. If you increase over this electrophile, the reaction rate is also increased. That means both of them are involved in rate determining step. 2 reactions should happen together. Okay? So that's why we call this reaction as SN2 reaction. SN2 reaction, it should attack at the same time. Attacking and leaving should happen at the same time, and there should be one type of transient state. Maybe planar structure, and coming in, leaving, and then all result is this position of S configuration is inverted. So inversion happens. During the SN2 reaction, configuration of a chirality center is inverted. Only that reaction happens. To that, nucleophile should approach from behind of leaving group. Then linear flow, electron comes in and then smoothly push it out. Okay. That type of reaction, what we call SN2 reaction. So through SN2 reaction, you have a nucleophile, you have alkyl halide. Alkyl halide, bluish color here, a little reddish here. Nucleophile, electron rich. It comes from behind and planar transition state. Transition state means you should have a double dagger here. Okay. Transition state. And then, as a result, this leaving group bring those negative charge and then project the form. If you draw those as the reaction profile, it has only one transition state. Reaction started here, and then over this transition state and go down. Similar pattern. Now, 2 cases you can think. If the product is identical, we can think maybe reactant, if the reactant is a little unstable, and reactant is more stable, unstable versus more stable, which one may be faster reaction? More stable or more stable or less stable? Which one may give you faster reaction? Less stable because it's a higher in energy, and reaction rate is determined by delta G, delta G star, delta G double dagger. That delta G double dagger is what? Activation energy. If this is less stable, then activation barrier is smaller. This is activation barrier. If it is more stable, then activation barrier is higher. In other terms, if the reactant is more stable, the less stable, then this is more reactive. Then reaction can happen faster. On this diagram, activation barrier is smaller. That's why it can go faster. If the reaction starting material is the same, reactant is the same, product is different. So two kinds. One is more stable product and less stable product. If that the reaction profile is like this, then which reaction is the faster? More stable because less activation energy, smaller activation energy. Okay. Of course, it's possible we can draw this the black line go higher and come down. If that is the case, the line reaction is slower, but thermodynamically it's more stabilized. So that means if you give enough time, anyway, the product will go to black line. That's a thermodynamic control. But kinetically, reaction rate-wise, the red line may be faster. Okay, so in this reaction, this attacks nucleophile attack here, and this is a second order reaction, and that's why we call this reaction as SN2 reaction. SN2 reaction, inversion happens. Now if you compare those SN2 reaction, nucleophile, the electrophile here, and nucleophile come here and attack. CH3 is kind of relatively open. One methyl group is a little steric hindrance, but still it's relatively open. It can come here. Now, two alkyl, primary and secondary. Secondary is a little cloudy. May happen or not. Tertiary, now impossible. There is no position you can go squeeze in to the reaction site. That's why if you look at those reaction rate. Reaction rate wise, it's a methyl group very fast. Primary alkyl halide still okay. Secondary slow. Tertiary almost no reaction happens. Okay. SN2 can happen very well with the primary. Secondary maybe or maybe not. Tertiary no way. That's SN2. Okay. Now if you look at this type of reaction we have seen in cuprate reaction and also the palladium catalyzed Suzuki coupling. In those reactions, if electrophile is alkyl halide is vinyl halide or phenyl halide, SN2 reaction did not happen. SN2 reaction should happen, nucleophile should come from behind and push this out. That happens only to tetrahedral structure, sp3 carbon. If it's sp2 carbon, it cannot happen. And this is also sp2 carbon, cannot happen. There's no room this nucleophile can approach here. That's why those reactions, when we had the cuprate reactions, reaction mechanism, we didn't draw this way. In the case, two motifs combined together to the metal, and then new bond is formed, and the metal was eliminated. Coupling to the metal, and then eliminated. Oxidative insertion and reductive elimination. So that reaction is a metal catalyzed reaction. Those are not SN2 reactions. SN2 reaction should happen on that carbon, and inversion should happen. It's only pure organic reactions. That's SN2. Now, step by step. All those SN2, for the nucleophiles. Nucleophiles should have high electron density. It can be negatively charged or neutral. Negative charge may be stronger nucleophile. Now, leaving group has anion. That's why if you start with a negatively charged nucleophile, product is neutral, reactant is neutral, product is neutral. But leaving group has minus charges. This electron was shifted to them. Reaction type itself, if you look at here, this is an exchange reaction, substitution reaction. If nucleophile is neutral, and still leaving group is negatively charged, then this is negative, originally neutral, then to get the charge balance, your product should be positively charged. Makes sense, right? Plus minus is 0, 0, 0, 0. The nucleophile can be either negatively charged or neutral. So if you look at this type of reaction, now this reagent we have seen before, acetylene, terminal acetylene, you could deprotonate this using what? Acetylene deprotonation using Na? Yes, NaNH2, sodium amide. Using that you can deprotonate and then make nucleophile. And react with the electrophile and attack here, push this out. Negative charged one, negative charged leaving group, and neutral. This is essential reaction. Inversion should happen. Now if you look at those nucleophiles, negative charged one is a stronger nucleophile, and sometimes amine group, amide is a good nucleophile too, but amine group is also act as base and nucleophile. Water is a weak nucleophile, but sometimes it is a very reactive reaction. Even water, in principle, it can act as a nucleophile too. So reaction rate, if you can look at here, these are strong nucleophiles. These are weak nucleophiles. Okay. More electron dense negative charged one is a better nucleophile. Makes sense. Now let's look at the leaving group. Leaving group, if it's more stabilized, then they tend to be more stabilized and there's a happy after leaving. That's why they become better leaving groups. HF, HCl, HBr, HI, the acidity going down, acidity is increasing or decreasing? HCl, HBr, HI, increase or decrease? It's decrease. HBr is a weaker acid than HCl. HBr is a stronger acid. HF, weak acid. HCl, strong acid. HBr, even stronger acid. HI, strongest acid. Okay? Acidity increase, that means conjugate base is more stable. That's why to this reaction, stronger acid conjugate base is more stabilized. That's why leaving group reactivity, this is better. And we just learned about the tosylate. Tosylate is even better than the best iodide. So that's why tosylate has been used to activate the alkyl group. And we have seen SaOCl2, PbR3, ocyl, those are alcohol activating groups. Okay? Those are good living group. In your textbook, it was shown like this, but this is more common. Less than TOS and TS, or minus this is tosy group. Either way, you can choose. Okay? Tosy group is quite good living group. Now, this reaction we have seen here, right? Last week we have seen this. So let's look at it. Originally, you have a chiral alcohol. Associated to this is intermediate. Attack here first, and then Cl minus was removed, but this is an unstable intermediate. And Cl minus come back and attack from behind here to make this. This step is SN2 reaction. Look carefully. This step is not SN2 because this one there is no carbon. SN2 reaction happens only in carbon. Now this way, almost the same reaction. Oil attack P, and then Br minus is removed, and then Br minus comes back from behind and attack from behind and generate this product. Alcohol to alkyl halide. Question. Chirality is inverted or retained? It's inverted. Why? There is a one SN2 reaction. In situ. Intermediate is unstable. That's why you cannot isolate this intermediate. If you put these reagents, you get alkyl halide from alcohol. That alkyl halide is inverted alkyl halide. One SN2 reaction happened. Tosylation reaction. If you add tosyl chloride, alcohol attack, and Cl minus is removed. And the tosylated intermediate, is it inverted or retained? Alcohol OH attacked, and the carbon attached to the oxygen was not attacked. Tosyl group is added. It's like this is tosyl group. SN2 reaction did not happen yet. That's why it retained. That's a big difference. Now, this is tosyl group. If it attacks, and then generate this product. Second reaction of SN2 did not happen yet. Okay? So just one step of tosylation, the configuration is the same as original alcohol. This is different because in situ this is come from behind and then inverted. Okay. So similar reactions we have learned epoxide before. Epoxide is a cyclic triangular structure. And then nucleophile, this can be activated by protonation. And nucleophile attack from behind and push this up. And the product is, there is connection still remained here. If it's just the OH group, protonate and attack, the water is removed. But this is connected to two sides. That's why this position, this is good, but the other side is still there. That's why product is nucleophile added alcohol. Position, this position is nucleophile added, and this position is leaving group is there, OH is still there. So hydroxyl epoxide intermediate is very useful intermediate to make alcohol with the nucleophile attack. Addition manner, syn or anti. Anti or syn? It should be anti. Okay, from attack behind and over. Okay, solvent effect. So we have seen. Okay, let's summarize it later. Solvent effect. If any species, either starting material or transition state, if there's any species is charged, then charged species can be more stabilized by polar solvent, especially protic solvent. Protic means proton generating solvent, which can be water, alcohol, ether cannot. It's alkyl-alkyl, there's no proton. Ester cannot. Okay? Proton generating solvent is protic solvent. If it doesn't generate the proton source, we call aprotic solvent. Aprotic solvent. Okay. So if this reaction, azide NC minus is also nucleophile, like a CN minus or acetylide type reagent, charge it, and then react with the neutral alkyl halide, attack and generate this reaction. Now this reaction, interestingly, water, methanol, their reaction is very slow. But aprotic solvent, it's a polar, but there is no proton source. Then reaction rate is increasing. How to explain? Why? Why? We are checking the solvent effect. In this reaction, what's going on here? Why, if you use a protic solvent, the reaction rate is becoming slower? Which one is stabilized here? By protic solvent, which one is stabilized? Among those reactants, which one is stabilized? Nucleophile is stabilized. You remember previously, reactant here, if that is stabilized, that goes down, and the status goes down. If the reactant state is more stabilized, the activation barrier is getting higher. By that effect, This solvent stabilizes more this. That's why the reaction is stabilized. So here, originally, this was aprotic. So this is an aprotic solvent. And then, if protic solvent is added, then this is stabilized. That's why this activation failure becomes higher. That's the solvent effect in SN2 reactions. Now, SN1 reaction. If there's SN2, in comparison there is SN1 reaction, this is a typical example. Alkyl halide react with the water. Water is usually poor nucleophile. But this reaction happened. And if you look at those reaction rate, methyl group primary is very slow. By the way, secondary is faster, 10 times faster. Tertiary, how many times? Million times faster. This cannot be SN2. Water is not good nucleophile, number one. Tertiary reacted with the nucleophile. Something wrong. This reaction is not SN2 because the tertiary water cannot penetrate here and attack these positions. So then they need to find different explanations. And the explanation is it's an exchange reaction, that's S reaction, but that reaction is not two molecules react together. This alkyl bromide that decomposed first, and Br minus left, and then carbocation is formed. Carbocation is formed, and then this carbocation is unstable. That's why the next reaction is quite fast. Whether it's a good nucleophile, bad nucleophile, it doesn't matter. And then react with the water and finish up those reactions. This type of reaction, rate determining step is the first step. Alkyl bromide self-breaking and generating carbocation is the only reaction step here. Only the rate determining step here. If this is formed, then the next step is activation failure is very small. So even with a very poor nucleophile, like water, it can just keep going. This reaction is so fast. This takes time to come over here. So this type of reaction we call SN1 reaction. And the result is alkyl halide into alkyl nucleophile. Product for the whole reaction seems like similar, but if you look at those reaction of the process, mechanism is quite different. So first step, this should be broken first, heterolytically. And then carbocation form. Carbocation planar. Then attack position of nucleophile, here and here, here and here, half and half. Even though you start from chiral starting material, if the reaction goes through SN1 reaction, you will get half and half racemic mixture. That means this reaction, in terms of stereochemistry, that's a bad reaction. You started with one single enantiomer, expensive material, but if that reaction goes through SN1, you get half and half mixture. It's a bad reaction. Now if you get this result, tertiary alcohol, tertiary halide, and adding water, originally alcohol. If it's 100% SN2 reaction, so you expect it to get S form, 100%. If it's 100% SN1 reaction, you expect 50-50. But you got a little more S, a little smaller R. How would you explain? Sojina? How would you explain? %% SN2 reaction, R should make 100% S. Okay? If it is not SN2 reaction, R should make 100% R. If it is 100% SN1, it should make half and half. Now you get 60% S, 40% R. How will you explain? 요즘 안 불러주시나요, 진짜?
둘 다 어때요?
뭐라고? 둘 다 아니면?
SM1이랑 SM2 같이
SM1 and SM2 is mixed. Okay? If it's a fully SM1, then you should get 50%, but there's a small amount of SM2 type of reactions also there. Leaving group should be left permanently, but still that's like nearby, hanging around as an ion pair. That's explanation. That's why there's a partial SM2, partial SM1. So this one nobody has seen, just we imagine. Okay. That's a mixture of SM2 and SM1 can happen. Then you get slightly shift to one direction. Okay. Now, those carbocation stability, we have studied it before. Primary, secondary, tertiary. Now here, allylic resonance, benzylic resonance, and even though there is resonance from here, radical case, allylic radical was most stable. Right? That's why you could get allylic bromination exclusively. But in this case, cation case, tertiary hyperconjugation effect is much bigger. So tertiary, secondary, and these guys are similar to secondary level, even though there is this type of resonance structures. Carbocation wise, primary weak, allylic or benzylic or secondary similar. Tertiary is still preferred. Hyperconjugation is a strong effect of more charged species. Radical case, allylic was most stable. So through this effect, now let's think about the leaving group effect. Leaving group effect is almost similar. So I was more of the better leaving group. Postulate was even better, but here it's similar. Now, in this case, water is quite a good leaving group. That means you have an OH group. By adding acid, you can proton it. And then that leaving group can be water can be removed. So that means you have a tertiary alcohol, you add the acid, and you can form carbocation. Water can be removed. Okay. So protonate here, and then water can be removed, then you can form carbocation, planar structure, and if the Bial attack, then half and half in both sides, SN1. Tertiary alcohol, HX, protonate, water removed first, and then X is added. Reaction, it's not attacking X from behind because it cannot attack this patient, not SN2. Carbocation formed first, and then react with X minus. Now solvent effect. In this case, if you have polar solvent, protic solvent, what do you think? Reaction can be faster or slower? Because which one is stabilized? Nucleophile is stabilized. Here, what is the nucleophile? If nucleophile is a charged species, it can be stabilized too. But here, sometimes there is a neutral nucleophile too, like water. In this case, what is the intermediate? Intermediate is a carbocation, charged species. To form carbocation intermediate, it's better to stabilize. So carbocation can be stabilized by protic solvent. So if you wanted to induce carbocation as an intermediate, it's better to use polar solvent, especially water-containing solvent, water or alcohol-containing solvent. Then reaction can be quite fast. Because the first step of carbocation forming is a difficult reaction. If this is stabilized, the whole reaction can be faster like this because of this activation delay process. SN1 reaction, if you have an option, then you make polar solvent. Now, we just summarized of SN2 reaction and SN1 reaction. Let's summarize. SN2 reaction. Reaction should happen between two molecules at the same time. Nucleophile should attack leaving group, leaving event should happen at the same time. That's why this molecule, both of them participate in the rate measurement. X has only one tension state, no intermediate. SN1 reaction, it should have carbocation intermediate. To stabilize the carbocation, it's better to have tertiary and very polar solvent. Okay? In SN2 reaction, if nucleophile is charged, then polar solvent actually deactivate. It's too stabilized. Okay? Nucleophilicity, more charged species is more negatively charged one is stronger. OH minus, amide, halide, those are charged, negatively charged, they are strong nucleophile. Water is weak nucleophile. Amine may be a little better nucleophile. Okay. Now, this nucleophilicity can help the reaction rate in SN1 or SN2. If you have a stronger nucleophile, reaction rate becomes faster in SN1 or SN2. SN2, what happened in SN1? It doesn't matter, because in SN1, rate determining step is a carbocation forming. Whether second step is faster or not, it doesn't change the reaction rate. That's why even very weak nucleophile like water also can act in SN1 reaction. Okay. Nucleophilicity is important in SN2 reaction. SN1 reaction, it doesn't matter. Leaving group, in halide case, leaving group wise, it goes down, the leaving group effect is better or worse. In halide goes down, leaving group efficiency increase or decrease? Increase. I minus is better leaving group. Okay. It's the same in both SN2 reaction and SN1 reaction. Tertiary group is quite good in leaving group too. Now stereochemistry. Tertiary group addition to the alcohol. Alcohol attack the tertiary and generate the tertiary as an intermediate. Chirality, inversion or retention. Actually, in retention, it didn't change. OH attacked tertiary and then intermediate is still there until it reacted with the nucleophile attack from behind. It's still retention. PBr3 with the alcohol. Product is alkyl halide. Retention or inversion? That's inversion. Because intermediate is unstable. Cl minus, Br minus directly attack from behind. One SN2 reaction happened on the carbon. That's why inversion. SOCl2, retention or inversion? That's also inversion. We learned only three classes: tertiary, SOCl2, and these are all same class, PX3 or PX5. Okay, these two give you inversion product. This gives you retention product. Okay, if you can understand this much, then you are more than half done for SN2 SN1 reaction. 100% inversion is the SN2 or SN1 reaction? That's SN2 reaction. Half and half, SN1 reaction. No change, that implies that there's no SN2 reaction here. Okay. So that is kind of summary of SN2 and SN1. Before we finish, let's review this one more time. Now here, nucleophile attack from northwest, coming down from behind, attack here, push this out. SN2 reaction. And product is inversion product, SN2 reaction. This attack coming here, but rather than attack here, if this is very crowded, maybe attack this. And this electron is pushed to this direction, pushed, two-step pushed. At the same time, it can happen. Then this is E product, elimination product. This is SN2. This one, E2. Because this is also base, and this one is involved in reaction rate. Okay. SN2 and E2. We are going to learn E1 on Thursday. E1, intermediate is same as SN1. What is intermediate? Carbocation. From carbocation, it has plus charges. It has two options. One option is meet with the nucleophile, matching, half and half, either direction. The other option is it give up one proton. If the carbocation, let's look at the carbocation. Okay, let's say here in this carbocation, if one proton is given out, then one proton is removed and double bond formed. Product-wise, E2 and E1 looks similar. Mechanism different. E2 is similar to SN2, and two molecules should react together like this. This is a good picture to see that. Come here, attack SN2. Attack, push this out, E2. SN1, form carbocation first, and then react with the nucleophile, SN1. Forming carbocation same way, and one proton is removed by forming double bond, E1. Okay? So this is the general mechanism of SN2, SN1, E1, E2. If you understand this relationship and those effects, living group effect, nucleophile effect, solvent effect, you learn half of organic chemistry. So I put up the question already. Start to solve the problem, and then don't miss the Thursday to summarize everything. Okay, that will be our last organic reactions in this semester. After this, we are going to move to characterizations. Mass spec, IR spectroscopy, NMR spectroscopy. Okay. Chemistry is until this week, so don't lose this chance. If it's not very clear, then practice now. Okay, and we are going to finish on Thursday. Okay. Any questions? If not, we'll do that.